Hi, this is Jonathan Gardner. I'm going to teach a course on electrodynamics. This is what I learned when I went to college and studied as a physics major. This is real electrodynamics. This isn't hand waving and smiles and happiness and pretending you know when you don't know. The book that we're going to use, and you need to get this even though it costs a lot of money, is Introduction to Electrodynamics. This book is written by David J. Griffiths. It's a great book. This is probably the best physics textbook you're ever going to find in your entire life. This is the second edition. The third edition came out shortly after I graduated. And there's a fourth edition coming out soon. You can find the second edition if you really want it. I don't believe there's too much difference between the different versions, and to be honest, you probably could get by without the textbook. You won't be able to do the problems, of course, which I think is a major part of learning how physics actually works, but you'd be able to learn at least some of the principles and remember them. What do you need to know? Well, if you want to learn electrodynamics, you have to be proficient in the following fields. One is algebra. You know, if you don't know algebra, you're just going to be completely lost. I can't emphasize that enough. You really have to go out there and learn algebra, get used to moving those symbols around. Another is calculus, but you'd be surprised how little you actually need to know to get through everything. So if you just understand the ideas of calculus, what the limit, derivative, and the integrals are, that should be enough. The third thing that you're going to need to know is some classical mechanics. Basically what you would pick up in your first year as a physics student, or that physics class you have to take as an engineer. So this is the F equals ma stuff, you know, 1/2 mv squared, some of the rotational kinematics, and some of the basic principles of how physics works. And the reason why you have to take that is you have to understand you know, what mass and velocity and acceleration really mean, and you kind of have to have a feeling for how physicists approach problems versus mathematicians. And the last thing you're going to have to need is you're going to have an open mind. Some of the ideas you're going to learn are completely different than what you think you already know, which is a good thing. When you learn something new, you hopefully eliminate something you thought was true but isn't. So with all of these things, you should be able to do well in this course. Section 233, Poisson's equation and Laplace's equation. So we know that the electric field is just the gradient, or negative the gradient actually, of the potential, the electric potential. So what happens when we take the divergence of E, or rather the divergence of this gradient? So the divergence of E, well, we already know that's going to be equal to the charge density over epsilon naught at that point. And this is also going to be equal the divergence of the gradient, of negative the gradient. So pull that minus sign out. So we have minus the divergence of the gradient of V. So we have basically minus the Laplacian of V. So we get the result that the Laplacian of the potential is equal to the charge density in space divided by epsilon naught. And this is known as Poisson's equation. All this says basically is that the potential basically accelerates. So it grows ever steeper where there's charge around. And Laplace's equation is just basically what you get if you take a region of space where there is no charge. This is called Laplace's equation. And all this says is the acceleration of the potential there is 0. So if it was increasing, it continues to increase. If it was decreasing, it continues to decrease. And if it was flat, it continues to be flat. So much for that. We're going to explore this more in Chapter 3. The other interesting thing is what happens when you take the curl of E vector. So that's the curl of minus the gradient of V. Well, no surprise there, that's going to be 0. So the curl of any gradient is, of course, 0. So in truth, you know, the fact that the electric field isn't curly gives us the potential in the first place. So this is basically stating what we already assumed to be true. Anyway, hope that really helps you.
This video presents Poisson's equation and Laplace's equation for electrostatic fields. In this video, we will review several concepts. The first is Poisson's equation, which is an example of a non-homogeneous differential equation, and Laplace's equation, which is the homogeneous version. And we will use Laplace's equation to solve a very simple example at the end. So we begin this discussion with Poisson's equation. And to arrive at this equation, we consider Gauss's law. So Gauss's law says that the divergence of the electric flux density field D is equal to the volumetric charge density rho sub V. Now we know that there's a constitutive relation between the electric flux density field D and electric field E through this relation, assuming that we are in free space. So if we substitute this into Gauss's law and rearrange things a little bit, we arrive at this divergence relation for E. We also know that the electric field E is related to the potential V through gradient. So we have this additional relation that we can now substitute back in to the relation that we have here for Gauss's law. Doing so results in this second order differential equation that we see here, where we now need to take the divergence of a gradient. This is not as hard as it seems, because we already know how to write, for example, the gradient of V, which we can do here. So there's a gradient operation on the right. And now we want to dot that with another gradient operator, or basically take the divergence. So I can just put another gradient operator on the left and a dot in the middle. And now we need to compute this dot product. So we know we compute dot products by taking the x component of each, multiplying them together, taking the y component of each, multiplying them together, and adding it to the result for the x component, and finally the same thing for the z component. So after we carry out this simple dot product, we arrive in Cartesian coordinates at this relation for divergence of gradient of v. And we usually abbreviate that with this del squared. And del squared is called the Laplacian operator, and we're going to be using it a fair amount to solving these problems. So now we have the second order non-homogeneous differential equation. It's not homogeneous because the right-hand side here is non-zero. So it's a function of the charge distribution. Now it's important to realize that the Laplacian operator looks different in the various coordinate systems. So here is Laplacian in Cartesian coordinates. We just derived that by successively applying divergence and then gradient. But in cylindrical coordinates, it has a different form, slightly more complex form. And in spherical coordinates, it's even longer. So be aware of the fact that the Laplacian operator appears differently in the various coordinate systems, much like divergence and gradient and curl do. Okay, so here's an example of a problem that we would like to solve. We have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were zero. In fact, the right-hand side is zero in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is zero, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is zero, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density, or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.